participants to kindly switch off their videos and remain muted throughout the talk. Please type your questions in the chat box of Zoom and YouTube as and when you get them during the talk. We will collect the questions and ask them at the end of the talk to our speaker. If the time permits, we will have some direct questions and interaction session with our sir. So now I would like to introduce today's event organizer, Mrs. Leena Bokil, who is NASA Honeywell Space Educator, Science Communicator, a mentor, and an inspiration to the young students like me. I will request ma'am to speak a few words on today's occasion and introduce our guest of honor. Over to you, ma'am.
Good morning, everyone. Happy World Space Week 2020. Well, this year's theme is Satellites Improve Life. So this is a United Nations event, and the designated theme is just what I mentioned, satellites improve life. So it's because of satellites, the communication, the advanced technology that even today in the pandemic era, we are able to communicate like this in a distant learning form. But then I must say that today's guest, the keynote speaker, Padma Shri Pramod Kale sir, he has been working on this even a few decades ago. Today, we are all using it commonly. So with the introduction that I have received, I have known Pramod Kale sir for many years because of my association with the IETE. But then this is such an illustrious, his achievements and biodata is vast. But then I must make justice to his biodata and give a brief introduction. So I'm sure many of you know, but then I would like to state a few highlights and salient features and his achievements in his career. Kale sir was born on 4th March 1941 in Pune, and he studied in Ferguson College. Later on, he went on to do his bachelor's degree in physics from the MS Baroda University. And then he went on to do his MSc Electronics from the prestigious Gujarat University, Ahmedabad. Kale sir, his profession actually has been a very long one, and his first job was at PRL, Physical Research Laboratories in Ahmedabad. And then he went on to join the Indian Space Research Organization, ISRO, where he has served for 3 decades. And his contribution to ISRO has been immense. So he has been singularly lucky, especially to have worked with Dr. Vikram Sarabhai sir himself and Satish Dhawan sir, Dr. APJ sir. He has had great colleagues to have worked with. He got selected at ISRO and he worked for over 3 decades in various top positions and profound leadership projects, positions. His first experience at PRL was on satellite tracking at PRL, where he had, done a lot of work on satellite tracking. And that is how then after he got into ISRO, he got the opportunity to work at various top-notch projects. So Pramod Kale sir was also part of the first Indian team of ISRO that was sent to NASA's Goddard Space Flight Center for training in the launching of sounding rockets in 1963, and thereafter in establishing the Tumba Equatorial Rocket Launch Satellite Station, that is TERLS. So the first rocket flight that took place in India, from ISRO, but from Russia, that was the Aryabhatta rocket later on, Aryabhatta satellite later on, but then the TRL launched from their own launch pad. On 21st November 1963, the first rocket flight was made with his contribution. And then, as we know, that ISRO has been into the INSAT projects, the remote sensing, and then recent times, in the recent decades, Chandrayaan 1 and then the launch of Mangalyaan and successful launches and projects, missions, and thereafter 104 satellites of ISRO, and then recently Chandrayaan-2. So even after his career at ISRO was like there till 1996, but later on also he has worked on various projects. His involvement with ISRO is still there. So some of his notable contribution to ISRO and the Department of Space have been like head of Electronics Division Satellite Systems, the Satellite Science and Technology Center at Thiruvananthapuram, and his major part of service has been at the Satellite Application Center in Ahmedabad, and as project manager, electronics, hardware, and television department, satellite instructional TV experiment at SAC, project director for the INSAT-1 space segment in Bangalore, mission director for ISRO's payload scientist missions, director of SAC Ahmedabad, director at the Vikram Sarabhai Space Center in Thiruvananthapuram, so on and so forth. So actively, even after his service at ISRO was over, he's still associated actively with them. And then also he has been engaged in teaching assignments, especially in the Gujarat University for the PG diploma courses in space applications, etc. And he continues to serve even in the Pune University SPPU projects and various other topics. And even back then, when he was actively involved in Gujarat University lectures for the PGD courses, back then the Doordarshan had telecast or transmitted his programs and lectures. So after retirement from ISRO, he served at the Global Wireless Technology Systems, head of Microwave Antennas Division, and executive director at GWTL. And he has been executive chairman at Exploratory Science Center in Pune, and he is the trustee of Indian Institute of Education, Pune, and he has been actively involved in the IET, Marathi Vigyan Parishad, so many of the institutions, and his list of awards is illustrious as well. Shri Hari Om Ashram Prerit Dr. Vikram Sarabhai Award in the 1990s, Padma Shri from the Government of India in 1984, R.L. Vadhva Gold Medal from the IETE, then Bharat Jyoti Award, the Front for National Progress, Aryabhatta Award from the Astronautical Society of India, Microwave Pioneer Award 2014, and Jeevan Sadhana Gaurav Award in 2016 from the SPPU, Pune's Pride Award for Excellence in Academia from the Residency Club, and so many others. He has published 20 papers and more in national and international journals. He has written and published a book, and you all must read it, Colors in Nature. And currently, he is the president of CASP, and nationally and internationally acclaimed NGO. So many of his awards and achievements have led him to become, even today, he is associated with Pune University, SPPU, and the ISRO cell. He's actively imparting knowledge to youngsters, and today he's here to talk about his experience also at the Satellite Application Center and his first-hand, experiences with the founder and father of Indian space program, Dr. Vikram Sarabhai sir himself. So many of his awards and accolades have been, inspirational to people like us. He has been inspirational to me and Hemil, and I'm sure you all are eager to hear from him. And I would also like sir to talk about his experience when Aryabhatta, the first Indian satellite, was made, and how today technology, I'm sure the fundamental, the underlying principles are the same, but still there's so much advancement in technology. So we are all keen to hear from Padma Shri Pramod Kale, sir. Thank you. Over to you, Richal.
Okay, so I'll request Pramod Kale sir to deliver his talk.
Okay. Namaskar.
Hello.
It was a lengthy but good introduction. After time, this World Space Week is really very, very interesting. Last year it was the Moon, the Gateway.
Good.
Next year it is going to be something different. This year it is Satellites Improve Life. What I would like to do is take a, just as a general review of what has happened so far, what can be coming up in the future also in terms of the applications of the space technology, how it has started, where it is leading to, and what lies in the future. I'll be sharing my PowerPoint presentation, and using those slides, I'll be talking about certain aspects of the work that has gone on. I'll be sharing the screen. Sometimes I can't understand as to why it is taking such a long time. Okay. Space has always fascinated the humankind. Many new things are thought about, many new things have come up also. The World Space Week is observed each year to commemorate the launch of the first man-made satellite of the Earth, Sputnik 1, on 4th October 1957. This year, the broader theme is Satellites Improve Life. We have been utilizing the applications of the space technology in our day-to-day life, and I'm quite certain that our day-to-day life has certainly improved when we have been using the space technology for all of our work. We sometimes don't even realize that whatever we are doing, somewhere along the line, there has been certain elements of the space technology that has come into that particular thing, whatever we are trying to do. To bring out a very interesting point would be that when the first satellites were launched, particularly the Sputnik as well as the Explorer, at that time, they had no other power source other than just only the batteries. So when the batteries ran out their life, the satellite also stopped functioning. And that is the time when people started realizing that, okay, out in space, we can actually generate electricity using the solar cells. So a large number of solar cells, practical solar cells, developed. Whatever was required for launching a satellite resulted in such a fashion that everybody realized that we have to reduce the weight, we have to make certain that they are reliable. So the reliability related things, optimization, things related to reduction in the weight, etc. Everything started because the space really required that specific property. And that is how the integrated circuits in electronics also started coming up. Newer materials got developed, particularly for the space technology related things, work. And I'll be talking about this particular broader theme as to how satellites have improved our life or how it is going to improve further also today. We see people communicating and using a mobile phone. We have to start going back into the understanding of the technology as to how the mobile telephones are working. In the initial period, it was all terrestrial communication. Then it became the mobile-related additional things. But when we look at people from anywhere in India talking with anywhere else in India or abroad, that's where the satellites started playing a major role. And suddenly there was a spurt in our communication systems way back in 1984-85, when large number of telephone exchanges started coming up, as well as that was the time when almost every day one new television station was brought into service. 1984, 1986, that particular time period. And that was possible only because we had the INSAT satellite functioning. And that really made the Doordarshan or our Indian television network one of the largest. And even today also, it is one of the largest networks in the world. The availability of the satellites, widespread communications also led to the availability of education everywhere. One of the very important things for the life, when we look at it, is access to water. This access to water, we were able to make certain that it is definitely possible because we were able to actually contribute using the space images for locating where the bore wells should actually be dug. And that particular technology I'll be talking about slightly later. During this COVID-related situations, now we are quite clear that our education, particularly whatever is possible for us today, is going to be possible only through distance education using television set or using a mobile device. And this particular situation is going to continue for the next 2 years to come as I see it. I look at it also as an opportunity, saying that okay, here is a situation, if we have to provide educational opportunities for everybody, then we must really go forward with respect to our distance education system. Even before a satellite was launched in 1957, applications of space technology were being defined by scientists, engineers, economists, industry professionals, and others. The ideas regarding space travel were there for a long time. Science fiction was replete with very, very interesting ideas. And the advantages of using the space technology for improvement in our day-to-day life were recognized very early. In 1945, before any large rocket or a launch vehicle was developed, Arthur Clarke had published a paper in Wireless World about geostationary satellites, which could be used for television broadcasting. See how far ahead he was in terms of the time. He had completely done the calculation as to what kind of an orbit would be required. There would be an eclipse, so during that eclipse, we have to support using the batteries. He also thought at that time that to get the signal from the satellite, 1 meter diameter type of microwave antennas would be used at homes for receiving the signals. Today, hundreds of millions of such antennas are used in almost all the countries in the world. In some places, we are able to use very much smaller, like 0.3 meter diameter type of antennas. And as newer and newer frequency bands are being utilized, I think we could be actually looking at handheld devices directly getting the signals from the satellite. Today, handheld devices are getting the signals from a nearby tower, but in the future, we could be looking at as to what can be done in terms of getting the signal for everybody directly from the satellites. Here are the first of the satellites, the Sputnik 1. on the left-hand side, and the Explorer 1. Sputnik 1 was launched on 4th October 1957, and Explorer was launched in the January 1958 by USA. The first satellite, Sputnik 1, when it was launched, I was a student at that time in Ferguson College. I was studying, and I was very much interested in radio communications. I had even built my own radio at that earlier than that in the XSC when I was there, capable of receiving only the local station. That was a crystal radio in those days. But what really fascinated me was that the signals from the Sputnik 1 were coming down in the 20 megahertz band or 15-meter band, and that was definitely available on our multi-band high-frequency normal radio sets which were available. And many of us, we tried to get the signals from the Sputnik 1 satellite at that time also. We were not successful at that time. Later on, when I started my work with the Physical Research Laboratory in 1960, satellite tracking, we did much more efforts and we were able to track, I think it was Explorer 7 in 1960 that had tracked. What Arthur Clarke had written at that particular time became a reality in 1960. Before this thing happening, there were communication satellites which were launched. The Telestar was one of the satellites made by AT&T. Relay was another satellite made by NASA. But SINCOM 1, that was the first satellite which went into a geosynchronous orbit. And what it did was that in 1963, as far as I remember, it was launched. In 1964, Olympics held at Tokyo. The first time live television pictures from Tokyo Olympics were seen in USA, particularly in the Los Angeles area, because that was a direct connection available. And this was what Arthur Clarke had predicted. If we want to get signals across oceans, we will need to use the satellites. And that is what actually happened. It resulted in the first Intelsat 2 satellite, or Intelsat 1 satellite, which was called as Early Bird. This is the next one is Intelsat 2. And the third one is Intelsat 3. This Intelsat 3 was launched in 1968-69. And we got ready in India for receiving the signals from the Intelsat 3, particularly for our international telecommunications. Before that, in India, we had established our experimental satellite communication Earth station at Ahmedabad, which was very important from the point of view of providing education to engineers and scientists from within India as well as from outside of India also. And that particular activity of imparting that education is still continuing. I had the opportunity to work on this major satellite. This is the Applications Technology Satellite. Back in 1970-71, at that particular time, this was one of the largest satellites to be launched. It had a 30 feet diameter, or 9-meter diameter antenna on the satellite. Now, this was a concept which was really way ahead of its time at the time, and that is earlier, which I showed you the picture like Intelsat 3, which was only 5 feet or 1.3 meters in diameter. That particular satellite was there, and the antenna on that satellite was just about maybe 20 inches or so, but that was good for coverage of the entire Earth. In order to receive a good quality television picture from that particular satellite, we would have needed some antenna on the ground, which was between 20 to 25 meters in diameter. The antenna that was built in India for that is located near Narayangao, Owing, for the Village Sanchar Nigam Limited. And that one was the first such, gave the idea as to what can be really done in the future if we could reverse the situation. And that is put a larger antenna on the satellite, a higher power transmitter on the satellite, and get signals to a receiver which is located in a village, which is a low-cost receiver. And this was the idea with which Dr. Sarabhai started out, that we signed a memorandum of understanding with NASA And we utilized this satellite finally in 1975, 1976 for that 1 year. And that really brought, for the first time, direct to community type of television in our country into the villages and other places. The time period that I'm talking about, 1967, 1968, when we started the work, at that time there was only one television station functioning in India. That was in Delhi. Dr. Sarabhai wanted to utilize television, bring it to all the people in India and utilize it for education and instruction. And that is why the experiment that was brought in was the satellite instructional television experiment. And uh, after conduct of that thing, we were going to go ahead with our Indian national satellite, which was again for television broadcasting. Here is that satellite on one side, and the other side is our television set with a small 3-meter diameter antenna made of simple aluminum mesh. At that time, we were working in the ultra high frequencies. We also conducted an experiment using the Symphony satellite, because the first experiment that we had gave us experience in terms of what we can do for the television broadcasting. We had to also do something for the domestic telecommunications. And we got this opportunity to utilize for the communication system using satellite system for the domestic communications. And that was an experiment called as a satellite telecommunications experimental project. And this was a satellite Symphony, which was developed by Germany and France together. And that satellite was available for 1.5 years or so for us. After that, this was our first communication satellite built in India. It was the Ariane passenger payload experiment. And this was our first communication satellite, which provided us with experimental communications for about 1.5 years or so. And this was followed with INSAT 1A and INSAT 1B. INSAT 1A was launched in 1982. It went into the orbit, but it had some problems and did not survive for more than about 6 months or so. While INSAT 1B, which was launched using the space shuttle, here in the photograph you can see that the satellite is being released by the space shuttle, and that happened in 1983. And once it went into the orbit, it survived for almost 10 years or so. That's 3 years more than its intended lifetime. And I was the project director for this, and we really worked very hard to get this thing going on. And then later on came the series of the satellites which we built in India and launched from India also. In the same time period, in the initial period, we had built the Aryabhatta satellite. That was a Indian scientific satellite project taken up jointly with USSR. And this was the first application satellite, was the IRS-1A. Before that, we had on the Bhaskara satellite, that we had a camera on it, but the data was not really very, very useful as what we had initially thought it would be. But IRS-1A showed the way to what is happening now. Today, the satellites which we are making, satellites which we are launching and using, are providing data not only for us, but also to large number of countries outside of India also. The panel of the United Nations had prepared a large number of documents in 1967-1968 time period, detailing a large number of space applications. Now, these applications were thought of not just only for the developed nations, but also for the developing nations. And most of these applications have now been realized. These applications or uses of the satellites and the information is received from the instruments on the satellites are making life really better for all the mankind. This is how Dr. Sarabhai had put it to us at that particular time, as well as for everybody. And that is, there are some who question, this was in 1968, he had said, there are some who question the relevance of space activities in a developing nation. To us, there is no ambiguity of purpose. We do not have the fantasy of competing with economically advanced nations. The exploration of the moon or planets or manned spaceflight. But we are convinced that if we are to play a meaningful role nationally and in the community of nations, we must be second to none in applications of advanced technologies to the real problems of man and society. And we were really inspired by him, and based on that, we had started our work. Today, we have achieved most of the goals set out by him, and we are looking forward to contribute in more areas. Certain applications require direct use of satellites, and a large number of applications have been thought out as application by utilization of the technology that was developed for space. That is, whatever we developed for space, how it could be also utilized to be on the ground itself. And I'll give some examples of it later also. Today we have numerous applications of both the types, and as a result of these applications, very large industries have developed. 3 or 4 major applications of space technology were thought out first, and the others developed later. Now, these applications were space communications, which I said earlier regarding what Arthur Clarke had thought about, and taking it up further, it actually got developed properly. And since about the very early papers also, when I studied later on, but yes, there were early papers as early as about 1954, 1955, as to what can be done when we are able to launch a satellite. Particularly, we could be looking at the Earth from space, and therefore we will be in a position to take even pictures of the entire cyclone developing. That is thousands of kilometers across, and that kind of a picture can then definitely tell us as to how that cyclone is progressing, where it is going to go ahead. So the meteorological Earth observations were one of the important applications that were thought about. And then came around 1968-69, the realization that from space, we can observe many things which are happening on the Earth. And what we are seeing, how it could be utilized for management, for exploration, for natural resources. Just as a simple kind of a thing that I would like to say, that when Yuri Gagarin had gone in space, and when he described certain things, what he was seeing, many people could not believe that, yes, from a distance of 300 kilometers to 400 kilometers, he was able to see those things. Same kind of a thing happened when Gordon Cooper, an astronaut from USA, went up in space, and when he described certain things, he was able to spot even the smoke coming out from a ship which was in a canal. But people thought that how is this really possible from that distance to be able to see? But when you actually do the calculations, yes, you can find out that you are looking vertically downwards. So you are not getting that much problem due to the atmosphere. And it is definitely possible to see these things. There were satellites by that particular time which were being utilized for reconnaissance, for surveillance by the defense or the spying and all other things. And those were getting the pictures. But at that time, the pictures which were coming, there used to be film cameras. The film had to be developed in space, and the pictures to be sent using electronic system. That was one way, or otherwise it would be the retrieval of the film itself. And 1968-69, the proposals started coming up about the Earth Resources Technology Satellite to be built by NASA. And again, I was very fortunate in 1969 to be in USA at that time, and I became a member of the first team which was looking at the remote sensing. Professor Pisharoti, Professor Dakshinamurthy. Pisharoti was from our ISRO at that time. Dakshinamurthy came from the Indian Agricultural Research Institute. Mr. Krishnamurthy from Atomic Minerals Division, and myself. We were the 4 people. We went around, did the studies, and came back and reported to Dr. Sarabhai as to what we should be able to do in the future. USA had earlier launched a satellite system called as a Navistar. Used to the Navy Navigation Satellite System, as it was also called. And these were the satellites which were in the low Earth orbit. The signals which were coming from the satellite were being received, and by looking at the Doppler frequency in that and reverse mathematics, it was possible, knowing the satellite where it was, you could work out if you get the signals from 2 or 3 different satellites as to where you are on the ground, on the Earth. And this was the kind of a navigation system that they had thought about, which resulted after that into the global positioning system, because everybody wanted to have a navigation system which works daytime, nighttime, whether it is cloudy, whether it is raining, and that's the kind of a thing which will require a navigation system. So for navigation and geodesy. So these were the 4 major applications which were actually thought about, and today many large number of applications of the space technology have now been developed. From the telecommunications or the space communications point of view, the first and most important use was the international and domestic space telecommunications. It was possible to have the international communications using certain cables. The transatlantic cables were there, but there were no such large cables across the Pacific or in the Indian Ocean area. And international communications, when I remember that as a student, when we were working even way all the way up to 1970, was dependent upon high frequency radio systems. We had a station located right here in Pune, near Pune, in Dighi. And Dighi was the transmitting station, and in Daund we had the receiving station. And these high power radio communication systems were the only systems which were available, and these were affected anytime whenever there was a solar storm. Certain times we do certain communications in the daytime, we had to change the frequency for the night time. All those problems were there, and they were mitigated by use of the satellite systems and our international operational system, which became operational as Intelsat. In India also, our station became operational in 1971-72. As I said that for television, radio broadcasting, the question was how we can actually use a satellite, and we did utilize that satellite in 1975 for the first time. Proved that yes, it can be actually done, particularly for the community, and that's why INSAT satellites were developed. And later on, today, we are seeing that we are getting almost something like maybe 600 or 800 channels coming from the space. I still don't know what people do with it. When you have got only one screen in front of you, what is the point in having 600 or 800 channels? But anyway, those are available. And we do require all these channels because when we consider we have so many different languages, so many different states, and if we could utilize it properly for education, certainly it will be really the best thing to do. The satellite communication systems, being wideband systems, were definitely possible to be utilized for data communications, for computer networking. And then when the internet came up, after that, it's definitely all the time available. It was very clearly recognized that for the maritime mobile communications, the only thing which was available was definitely the space communications. There was no other method with which we could have mobile communications, particularly in the maritime or the across the ocean, or when a ship is in the ocean. Same is the case with aeronautical systems also, aeronautical mobile. For the land mobile also, people were in the initial period looking at as to what can happen in terms of successful communications. It is definitely possible to use the satellites, but then the cost of using a satellite communication to that extent is very much more compared to what happens when we use the mobile communications. The number of receivers or number of mobile users being very large. One very successful satellite communication system for the mobile, land mobile, which became successful, and that is, it's a combination of satellite communications and the GSM communications. That is the Thuraya satellite, in which the handheld receiver that we have first looks for GSM, and if GSM signal is not available, then it switches over to the Thuraya satellite. And that became a very successful mobile communication system for the land. In Japan, particularly for Tokyo, they were looking at whether we could have mobile communications from the satellite, because what they were finding out, the density of the buildings is so high in Tokyo City, all these high-rise buildings which are there, that the normal GSM systems also fail in that kind of a situation, because the communication is in a horizontal way, and in the horizontal way, all the buildings are there. If the at a high elevation angle, if a signal comes from space, they were looking at it. Suddenly, it functioned, but I don't think that economically it really made sense. But some of the Japanese systems do depend upon the satellite communications for that. The same communication systems, communication satellites, could also be utilized, and we have seen there were proposals from the navigation related things. The navigation related thing, uh, global positioning system, as a system which was started by USA, it became very, very successful, but it requires at any given time between 21 and 24 satellites to be operational. Because they had certain political differences, Europe had decided to go ahead with their own system, that was the Galileo. Russia went ahead with their system, the GLONASS, and the Chinese also went ahead with their own system, the Meteorites. In India, we took the decision that we can use geosynchronous satellites, some of them geostationary and some of them geosynchronous, but in inclined orbits. And that's how we developed our Indian region navigation satellite system, IRNSS, which we are named as the NAVIC. It's really a fantastic system with which we can do, because this is a second or third generation kind of a system, and we are able to add certain messages also in the navigation. So when the fishermen are out in the sea, apart from the navigation, they also get certain warnings regarding the development of the storms, of what is happening around. The navigation satellite systems, the Geostar or the Navstar of the early systems, you can get the signal from them and monitor it for not just few seconds or few minutes, but monitor it for over a week. It could really result in, for the first time, getting the accuracy or the position determination on the Earth right down to 5 meters. That was the first time that it happened in 1969-70, when we actually started getting the signals and using it in that particular fashion. And that is how people started depending on the satellite navigation for geodesy also, for very accurate determination of your own position. Today, yes, it has gone down to less than 5 meters or less than 10 meters. Within few seconds, we get that kind of an accuracy. One of the interesting things that happened in the satellite communications was that using some of the low Earth orbiting satellites, it was possible to add a package into the satellite where it will receive a signal which is sent out in case of an accident by a beacon, a radio beacon. And that signal then can be amplified and sent back to the ground. And that satellite then, the signal can be then received by various local user terminals, as we call them. And this became the search and rescue, or the SARSAT system. And India became one of the early part of this particular SARSAT system. And today we have such systems located with two of our ground stations working, one in Bangalore and I think one in Lucknow. And any aircraft accident, if the aircraft is carrying a proper beacon, or if there is an accident in a ship, or even people who are going into the mountains, yes, it is definitely possible to get the signal and make certain that rescue can happen. We added a package in our geosynchronous satellites also for this beacon to be received. So when the satellite is not moving, we cannot get the position determination, but we can at least get the first alert that an accident has taken place and then take appropriate action. Here you see an image where we were receiving the signals from the satellite during 1975-1976 for the satellite instructional television experiment. And then this was followed up later on once the Doordarshan started expanding. People establishing an antenna anywhere, wherever they can, in the desert area, using it for computer education, using it as a small BPO also. We developed a satellite which was basically only for education, as an education satellite, EduSat. not utilized properly, but yes, our objectives were there, providing effective teacher training, supplementing the curriculum-based training. This EduSat network was functioning in extended C band as well as in the KU band, and it is working in some of the states. It's very successful, like Gujarat and Rajasthan, very successful. Karnataka is very successful. It's a very simple terminal which is required and a small TV studio. Again, let me look at it as to what is happening in the current situation. Currently now, people are using their mobile phones because the mobile phones have got excellent quality cameras. They don't require the professional studio type of a camera, but yes, certainly it is possible to use it in that fashion. The use of the satellite communications brought us into a totally different area, and that is, there is a camera that is available, a good quality camera, voice is available, so it can be utilized for telemedicine, such that any person can consult a doctor there, or that person sitting there can consult a specialist somewhere else. And this telemedicine project got developed using the ground systems as well as the space systems. Just look at the total thing that happened about. Sorry, what? Something went wrong?
Yes, sir. I can't see the presentation.
Just 1 minute. Let me see what is happening. Is a problem here.
Share screen.
Just a minute. It is starting up.
Okay. Yes.
Are you getting now? Hello?
No, sir.
Not yet. Yeah, it's not sharing yet.
It started here.
Uh-huh.
Mm-hmm.
The share screen option.
I'm sharing it.
Mm-hmm. Yes, it's back.
Yes,
Now we
sir.
see.
Is it back now? Okay.
Yes, we can see. Great.
Hello.
Yes. View slideshow. Yeah, I think we
Okay.
correct. Yes.
All right.
Yes, sir.
So okay. The idea was that we have these various islands, particularly the Port Blair, the Nicobar, Andaman Islands.
Mm.
The patients from there, they can directly consult the specialists in the Apollo Hospital in Chennai. So the people from Lakshadweep Islands, they could connect to the specialists in Cochin, or patients from northeastern region, they could communicate directly with specialists at the All India Institute of Medical Science in Delhi. Same is the case with our border areas in Kashmir also. But one of the very innovative use that has happened, which is very important, is that when there are no patients and when the system is available, the same system is used for continuing education of our doctors also. And there is a continued very good use which is coming up of the telemedicine system that we have. This telemedicine system has now been completely strengthened and it is functioning very, very well. This is specialized, even the telemedicine van, only for ophthalmology. That's for the maritime, land and aeromobile kind of a system that our satellites are functioning. Or for our defense forces, they have to. The communication system is very, very important from our well-being point of view or life. And finally, one of the largest satellites with large antennas that we have launched is the GSAT-6, in which that antenna is large enough that directly a single mobile phone can also communicate. And this kind of a system is being utilized for some of our VVIP type of communications. The Earth observations that I was talking about, question is what we can see and what we can actually then look at, understand it properly. So now the first and the most important application which was seen was if we can get proper images taken by our good quality cameras, we could use it for developing all the maps which are necessary, and that became the cartography kind of a mission. And if we can take the pictures from two different locations in the orbit, we can actually make it into a stereo imaging system. That stereo imaging system then allows us to determine the height of any specific scene that we are seeing, and therefore we can then map the complete system. Out of this photographic images as well as the stereoscopic images, what can be developed, which is known as digital elevation model, and that is the one that is continuously now being utilized for most of our work, whether it is urban related things or whether it is outside rural areas. We can go through how the land is actually being utilized, how the snow cover is developing, how it recedes. The most important aspect of monitoring the snow cover in the Himalayan region is that from there only we can find out how much is the snow, and then we know from that how much water in the next summer we are likely to get through our rivers. So for water management and water resources, it becomes a very important system to be developed, and that is how do we monitor the snow cover. Forestry. If we can map the forest properly, we can find out how the land is being utilized, how it is going to impact in our future also. And the forestry related things actually today it is continuously being utilized. But if we started looking at it from more and more into the water resources, fisheries, potential fishing zones that we were able to find, the minerals, how even from that distance of 1,000 kilometers when we take an image, the spectrum signatures that we get from that thing, we can find out what minerals could be present. We can monitor the pollution, how the urban systems are developing, how the urban slums are developing. And for that thing, we require geographic information systems and geomatics. Very high accuracy measurements taken place using the space system, and use the space applications, the Earth observations, particularly for the disaster management. We can do it from the point of view of surveillance, reconnaissance, from the defense point of view, early warning systems which are required for the forest fires. So the Earth and the ocean constantly keeps on as a dynamic system moving, the tides, the streams of the large water flow in the ocean, detection of cyclones and storms, detection of large sea waves, storm surges and tsunamis. Today, our entire system is completely functioning. Now here, one is a question of Earth observations, and second thing is utilization of satellite communication system to collect the data from remote platforms. The two things, when they are put together, that is the one that is providing us with the early warnings for the tsunamis also, as well as the pollution monitoring. Now, here is a very interesting image of the Earth developed, particularly of India developed using false color, and it's a composite image, not taken at one at a time, but multiple images are fused together. And the red color that you see here indicates the vegetation. So in 1968-69, that particular time period, when the infrared color film was developed, particularly this is the infrared portion of in the sunlight. Even the daytime, when we take a picture of, say, or when you look at a leaf, vegetation, we see that leaf is a shiny surface, and that shiny surface is going to reflect the infrared. So if we were to take the near infrared or that kind of a picture, the question was, what is the color that we should be assigning it in a color film? And what was decided at that time was that in the nature, there is nothing red in color which is naturally occurring. So if we want to use it as a false color for the green, which is good coming from the infrared, then we should be using red color. So this red color that you see is indicative of vegetation. The light that is reflected, which is coming from the sun in the infrared light, and that's the one that is being now utilized as a false color composite. We can see the entire country or entire globe also in this fashion. And here is a composite, same way, but only of Gujarat, developed using the IRS images. Look at the water that you can see here, and what is happening here is that along with the water, we are able to see the sediment that is coming in from various rivers, and that's the one that allows us to find out as to how far these minerals are going to spread, whether it is pollution or whether it is actually useful. And yes, from our exclusive economic exploitation zones, it is definitely possible for us to utilize this kind of a data for the future related things. One of the most important things which happened around 1987-88 time period was that we had a terrible drought condition in Gujarat particularly, and we were looking at it, looking at all the knowledge that we have about where the water could be on the ground, underground, so we can actually find it out. It's not easy for us to detect water which is underground using satellite image, but using satellite image, it is definitely possible for us to find out where water could have been there earlier. And that's the kind of work that went on. And we developed the complete system for that thing under the National Drinking Water Mission, provided the hydrogeomorphological maps for the government, and they are continuously being used. One of the first things that happened was that earlier, the success rate used to be less than 45 to 40% or so for the tube wells that were being dug up. By using the technology, the methods which we developed, we brought in the first year itself, the entire success rate went beyond 80%. And then today we are at about 96% kind of accuracy. If we were to take a review and say that, okay, here is, you'll get water, certainly we'll find water there. But we cannot yet tell what will be the quality of the water. Is it drinking water capable, potable or not? That's a separate issue. But basically we are able to find water, and that's through the Earth observations. Using our images which are possible in the initial period, we have 23 meter resolution, then 5.8 meter and 0.8 meter capability now with stereo capability also. Here is the image of Khadakwasla in Pune. As you can see, the dam. We can continuously keep every dam under surveillance using our images which we get. This is the university circle, all the roads leading to that point. When we look at what kind of applications can be there are all different types of applications. Once you start getting the images and the data, you can do quite a large number of new developments, particularly when we are looking at as to what can be done, and there are enough number of people working in a team fashion. As a teamwork, yes, we could develop these different types of applications. One of the important thing has always been as to whether we can actually look at and monitor the drought, whether the drought is going to take place, what it is going to be there, how it is going to impact us by looking at the vegetation index. Now here is an image of the fire that took place in Devanar, and it was possible to be detected on every one of our satellites also. But how that smoke flows, and from that thing we can find out where the pollution is likely to be spreading due to this. Same thing was actually seen in some of the earlier images also. The plumes coming out from our thermal power stations, we could find out, we could look at to how some of the farms were getting damaged because that plume, depending upon the wind. A very interesting thing that got developed was that as we were looking at the infrared data of the ocean, the infrared data of the ocean indicated that there were certain areas where there was cold water surrounded by hot water. There was hot water somewhere and then surrounded by cold water. At the boundary between the hot and cold water, we get thermosiphon type of effect taking place. And that is the dead material which is there on the seabed starts coming up, upwelling, and then it starts coming up. The fish know that's where it is happening. So they go there to eat that material. If we could know where such a system is happening, we could take that information and give it to our fishermen. And that is how this was called as a potential fishing zone forecasting. And this system, the initial period at the Space Application Center, we started working with it. The experiment, we ran it for about a year and then made it into an operational system. Today it has become completely operational for Gujarat, Maharashtra, Goa, Andhra Pradesh, and Tamil Nadu. It's a fully operational system. Some of the forecast is being done from Ahmedabad, certain things are done from Hyderabad. But yes, this is something which is happening. From the ocean color also, we can then find out where the biological systems are happening, where the material is going to be available for the fish and the other marine animals to use it. And that is the one that helps us in again defining the potential fishing zone. We can get so high quality pictures, we can actually use it for mapping. You can actually look at it as to how the urban systems are developing in terms of the town planning or urban planning. This is a new railway station at Kishangarh in Rajasthan. The initial Earth observations way back in 1960 itself, people were thinking about was it should be used for meteorology. And that meteorological satellites came up. The first satellite to be brought out in those days was the TIROS satellite, the television infrared observation satellite. And that satellite started giving in the visible images as well as thermal infrared. The infrared is the one that then helps us to get the images in the night time as well as from the water vapor also. By that time, about 1967-68, it was possible to put a camera on the camera or a scanning system on the ATS-3 satellite also that provided us the picture. And the first satellite which was getting developed at that time was the Synchronous Meteorological Satellite, SMS. And similar experiment was going to be there on our ATS-6 satellite also. We definitely decided to go ahead and put such a system in our INSAT satellite also. So today, that particular system is functioning. So from 1983, I would say September onwards, every day more than 20 pictures we are getting of the Earth, total Earth. And if we can take more images depending upon how repetitive we actually want it. We take sometimes every 5 minutes an image if a cyclone is developing. The meteorological satellites also provide us information for the oceanography, for the thermal infrared, the visible color, as well as the environment. Visible color basically give us the information regarding the biological systems. To support all this system for the meteorology, we require automatic data collection platforms. So these data collection platforms can be on the ground or could be on the sea-going systems also. And we measure temperature, humidity, pressure, wind speed, wind direction, rainfall rate, cumulative rainfall, the sunshine, the ultraviolet intensity, the water current, water level in the rivers, snow cover, snow depth, as well as air quality. And this data, in the initial period, we started with some 100 such systems. We went to the next level. Today, more than 1,000 such AWS systems are functioning. In the initial period, we had our INSAT satellite carrying the meteorological package. This was then added. It was decided that we should then now have, everything is successful, so we should have our own meteorological satellite dedicated for meteorology. And the first satellite which got developed was then named as Kalpana, because by that time, Kalpana Chawla had died in the accident, on the Columbia accident, as far as I remember. And so this was a satellite named as Kalpana. It is functioning even today. Then INSAT 3D, INSAT 4, all those satellites are functioning. And in the future, we are going to have much higher resolution cameras going up in the space. This particular camera systems, what we have, we can completely detect the cyclones, predict, and every time when we detect a cyclone, we keep on informing it. And for that thing, we have a disaster warning system also, which is dependent on our communication satellites. So here is a very interesting picture. This was taken sometime in February, as far as I remember. You can see the entire globe, as well as you can see the animation as to how the clouds are moving. See now today in the morning, this is how the system was, and you can see that some of the clouds are moving in the opposite direction now today. So we can continuously keep on monitoring, and by taking multiple images, then we can develop it into an animation system and make this thing work and actually predict what is going to happen. Our prediction system has completely improved, but just only getting the cloud cover, cloud pictures is not enough. We need to get more and more data regarding the water vapor and regarding some of the pollutants. Some of this work, we also have the radar sat imaging satellite, and that is taking the images in the daytime, nighttime, under cloud cover. Because if we want to do anything as a work in the northeastern region, we know that the entire state itself is called as Meghalaya. That is because 90% of the time it is completely covered under the snow cloud cover. That's our Indian region navigation system. One good thing that has happened is that I'm able to get these two such receivers, and they're being used by our students in the university so they can do the experiments using these receivers. A very interesting thing that happened was that from USA, the Planet Labs, they had approached ISRO, and we launched 104 satellites in one of the missions. I was very much interested in the satellites also, so during my one of the visits to USA, I went to Planet Labs because one of the students had arranged a meeting for me there, and I saw how they were making these satellites, each weighing only 3.5 kilograms or so. But I saw that entire system, and I was very, very impressed how people can actually work in such a small satellite to be developed at such a low cost. Space applications are in the other directions also. That is, we could use the zero gravity, no convection system, particularly for the preparation of newer alloys, better growth of large crystals, better synthesis of large or long chain molecules for pharmaceuticals, 3D printing of metallic and non-metallic objects in space. People are talking about it. It looks very, very simple, but getting the 3D printing going on in a zero gravity condition is difficult. One of the things that has happened is that the International Space Station, which was supposed to be really phased out in 2022 kind of a thing, is now going to continue to 2027. So they have decided to go ahead and utilize the International Space Station for the commercial purposes. So optical fiber Manufacturing in space is one of the things that they are looking at it, but Zebulon trifluoride glass is actually developed in space. Once it comes back on the ground, when we make the fibers out of it, the attenuation or the way the signals die down is very, very less. And so we could have very much longer distances between our repeaters. When we look at the space-related things, obviously we require food there for the astronauts. So what kind of food is required? All kinds of conditions are there. Appearance, it should be as normal, normal taste and smell, easy to digest, low in starch, no refrigeration should be required. All these conditions are there, and the food existing had to be developed, and was developed. This is the kind of food which is today. If you were to go to some of the museums and their gift shops in USA, you will find this is available there in that place. On the International Space Station, vegetables are being grown, and I think one of the latest capsules that went up to the International Space Station had carried the seeds of packages also. When Rakesh Sharma went up in 1984, the question was there as to what food Rakesh Sharma is going to get. So the food that was required was actually developed at the Defense Food Research Laboratory in Mysore. The same laboratory delivered food for ISRO payload scientists. Technology has now been transferred to many industries. The food which got developed in the initial period also supported all of our Antarctica missions also. And now the food included chicken tikka, chicken biryani, yogurt, upma, suji halwa, etc. That prepared, ready-to-eat food is also distributed as relief material during natural disasters. And the food prepared at DFRL is used by our Indian Army. It is also used in our Antarctica expeditions. Let me conclude by saying something from Pramod Batra. When you reach for the stars, you might not actually get one, but you will not come up with a fistful of mud either. Thank you.
Thank you so much, sir. Thank you so much.
Thank you very much, sir, for such an insightful talk. And not all of us are from the electronics, telecommunication, engineering stream. There are multifarious and multidisciplinary students, the audience. But I'm sure they have all understood this very well because you have made it very simple. And in a few quick questions, I'm sure students would like to know how today's students can contribute to making their own satellites like nano, femto satellites, and for what applications. So a few questions we can take, I'm sure.
Participants, I would like to raise, I will request you to raise the hands and then you can ask your question to sir.
Okay, please go ahead.
Yes, quick.
Anyone from the audience?
I think, Richal, you could start, and some Prachit and others have some few questions too.
Yes. Hello, sir. So I have, yes, sir. I have recently completed my bachelor's in mechanical engineering. Currently, I'm working in Ayuka as a project student in LIGO India team. And you said that you have some 2 receivers in Pune University on which your students are working on. So is there any chance wherein I can see the setup, I can meet those students and have a talk with them?
Right now, there are no students there because I think COVID situation, this has stopped us from doing. But as soon as we start our work again, please get in touch with me. Certainly, you can.
Thank you so much, sir. I'm so much interested in that.
Yep.
Yes, sir. Prachit, do you have any question?
Yeah, but I think there's one in the chat. Should we take those first? Could you?
Yes, sure.
Yeah. Okay.
Okay. In the chat box, we have Sir, can you kindly provide some good research problems for AI-based air quality predictions using satellite?
Yeah.
Basically, what we have to look at here is how you will be in a position to actually develop, first of all, a model. How are you going to be able to model the airflow in a given area? What would be your grid size that you are looking at it? The most difficult problem has always been how do you define the boundary conditions in the grid that you have? The time changes due to the solar insolation, the temperature changes, and the directions also change, and therefore the flow that is there is constantly keeps on changing. If you are looking at the artificial intelligence type of a thing, first of all, the most important thing which I have seen about the air quality is to look at the aerosols. The aerosols that give you the information regarding the pollutants itself, so from where they are coming. This is one aspect of it. Second thing would be you require multiple points, at least giving you certain amount of data using a wireless network, wireless sensor network. The amount of the nitrous oxides, and those are the first and the foremost thing which happens due to our vehicular pollution, and the aerosols come up due to the dust particles, due to the unburnt fuel. If we know what is it that we are looking for, then you can start looking at it, how to detect them and how to then predict what is going to happen. We have seen recently, particularly this COVID situation, once the vehicular traffic was less, the air quality suddenly improved in less than 8 days or 10 days. We saw that there was a definite improvement. So we know where the source of the pollution is. The question is, how do we actually model? And we have to take into consideration the time of the day as well as the amount of traffic. So we have to actually make the proper modeling of the input. There is input which is coming from the vehicular traffic. Yes, certainly it is possible to do so.
Okay. Uh, uh,
Richal, Ninad has some internet problems. He's asked if you could read out his questions.
okay, sure. Let me just. Siddhesh Deshmukh, sir, you can unmute yourself and share your thoughts with sir.
You say that? Yeah.
Deshmukh,
So
sir,
we
can
are
you hear me? Okay.
we are not getting his voice. Okay, here is one question, sir. There is one girl, Aditi Pandey, who is asking, can we do something about the space debris mitigation? Is there ISRO's any mission or project that takes care of this, or in the future? Can we participate in doing this? Because these students have done some research paper they have developed and with my guidance, and they wish to do something practical as in an application to take care of this particular challenge.
This is what says debris related things.
Yes.
Okay. Says debris, what I have understood, what I have gone through, where it is, yes, we know it. Some of it we can definitely track using the ground system radars, whatever information we have. Certain things can be done using optical telescopes. The most important thing is, what do you do about it? Can you actually move them away? Can you destroy them? If there is a debris, you try to destroy it by exploding something, you're going to create more debris. So that's not the way it can actually work. So the only way we can actually get rid of some of the debris is by using a high-powered laser located in space, which pointing towards a debris particle will result in actually vaporizing it. It should become as small that it no longer remains a threat. Because all these objects which are there, you must realize that they are moving at a speed of 7.7 or 7.8 kilometers per second, and their collision is going to be with any another object still will result in more than 10 to 60 meters per second. Now, that kind of a thing can definitely destroy a satellite. And so we have to be extremely careful with debris related things. People have talked about collecting the debris, but after collecting, what are you going to do with it? That's the next question that comes up all the time. So one is the mitigating. First important thing is how best we can actually know where the debris is. And we can predict, once we know where it is, then we can predict how its orbit is going to keep on changing, because it is important for us to find out as to when it is likely to re-enter the atmosphere and pose a danger to our civil aviation as well as in population on the ground. It has happened when the Skylab came down or when the Mir station came down, yes.
We have another question. Sorry, sir.
Go ahead.
Yes.
Okay. We have a question. From where can we get the bulk and free satellite data and meteorological data for India and the world for research purposes?
As far as the remote sensing data is concerned, you can get it as far as India is concerned on our ISRO's platform called as Bhuvan. And for the meteorological data, you will get that particular data which is freely available on the imd.gov.in. That is one of the things. So certain amount of data is available with the World Meteorological Organization. For the whole of the world, everybody sends the data there. But if you want to get a higher resolution data, then you must have a proper contact with the India Meteorological Department and get the data. Certain amount of data is available even with the CDAC here in Pune, because they have got a good collaboration which is going on. Certain amount of data you can get it from the Atmospheric Science Department, also from the Pune University as a starting point.
Okay. Another question is, what methods are used to protect space satellites from micrometeorites? Are there any long-term effects?
Well, with the micrometeorites, there is no protection other than the fact that yes, we have to make certain that whatever materials which we are using, they are such that when they are impacted by the micrometeorites, two effects which we always see is the abrasion that takes place. Now, this abrasion affects the very thin films which we use for our optics, or any of the thin films which are used on the materials. So we test them on the ground and predict as to how long they can actually last. What would be the effect of the radiation on it? There is no such thing as a protection against micrometeorites, but we have to be absolutely certain as to the materials which we are using do not degrade beyond its usable point during the lifetime.
Okay. So here is one generic question, sir. The youngsters would like to know, how can we participate or collaborate with ISRO or even Antrix Corporation, because there are some startups as well. And how could we participate in the future missions like Gaganyaan, Shukra, and Aditya mission, and so on, and be a part of it, just like what NASA does? I think
what I personally think is of the following nature, that ISRO has a very large program called as a sponsored research program called RESPOND. And the RESPOND program, any university can actually participate in that by actually making a proper proposal and getting it through. So when somebody is looking at that kind of a system, yes, when they have gone out the university, they formed their own company, so then they became a commercial entity. Yes, they have to also then propose as to exactly what they would like to do, how they can contribute. They have to really participate in the, what should I say, the technical tendering processes and all other things to be able to do so. Yes.
Yes, and
as students who want to make a satellite. Recently, I talked with the students here at Anandi campus of this MIT, students also. One of the things what I'm finding out is try to define what the satellite is going to do. Because now ISRO has already funded, it started with the ANUSAT from Anna University. There was this satellite from IIT Kanpur, IIT Mumbai, satellite made by the College of Engineering here in Pune. Turned out to be the best out of all these things, the Swayam satellite. Even though it was just only 1 kilogram in weight, it actually functioned. For the first time, we have seen a student satellite of this nature completely functioned throughout its lifetime and met the communications as well as the attitude control objectives. So they had a very good plan. They managed it properly, even though it took more than 6 years or so. so many changes happened in the project managers, the people who were actually working. The faculty did guides. When a student satellite of this particular nature, you have to have some very specific objective for which you are making the satellite. And I think first say that the alumni of the College of Engineering, they supported very handsomely by contributing towards making the clean room, making various things available.
Yes.
Prachit, I think you have the question on the similar lines.
We are also getting, the time is getting now.
Yeah.
Yeah.
We'll take a last one, I guess.
Yeah.
I think what I would like to suggest is that if there are any other questions of this particular nature, they can direct the questions to you, and then you can send it to me on my email, and I'll answer them.
Sure. Oh, we'll do that. Sure.
Yes.
So I think last question by Prachit we'll take, or we'll stop.
If you can take.
I saw that Professor Ravi had some question.
Yes.
Sir, could you please unmute yourself, Professor Ravi?
Sir, good morning, sir. I am Ravi Kumar.
Good morning.
And I was in SAC in 83.
Okay.
I am very fascinated and associated with ISRO and satellite programs. And I worked with Dr. Sankara,
Okay.
OPN Color, sir. And I had some papers also with them.
Okay.
You on screen and listen to you, and I am very impressed by the talk, and it was excellent. I would like to meet you personally after this corona and do something along with Leans. We had some student programs to bring the students who are interested and not able to access satellite programs, rocket and space science. So we want to do some bridging work. I would be meeting you. Thank you, sir.
Certainly. Most welcome.
Thank you, sir.
Thank you, sir. Yeah.
Okay. I think then we are at the end of our session.
Fine.
I will just like to give a vote of thanks. Am I audible?
Yes, you are.
Okay.
You're audible.
Yeah.
Okay. So I will just like to thank our guest of honor. I would like to really thank you so much, sir, because you have been an inspiration to all of us, and we are really looking forward to talk to you and have some really good projects hands-on, because we are also planning to work in space sector in the future. Prachit Kamre is amongst us, and he is currently a student in TU Berlin in space, taking a master's course in space application. Yeah. So thank you so much. I will also like to thank Leena ma'am for arranging such a nice event and putting us in contact with Pramod Kale sir. And thank you so much, technical team, Prachit, Ninadan, Soham, for doing a YouTube live and for the Zoom call. Thank you so much, participants, for joining us today. You can also watch this lecture on our YouTube channel. It will be available to you in 2 to 3 hours. So thank you so much. Leena ma'am, do you have to say anything?
Yes, to conclude, first of all, thank you very much once again, Pramod Kale sir, for sparing your valuable time and your insightful talk and interaction with the youngsters, and such a great inspiration, not just to me, but this future generation. And I'm sure this will go a long way in nation building. And they're all space enthusiasts from various fields and all wanting to do something and contribute to the nation. And just like what was envisioned by Dr. APJ Abdul Kalam sir, Dr. Sarabhai sir. So this is a dream, and it's a dream coming true. And what was yesterday's fiction is becoming today's reality. And I'm sure the technology will spin off. And these students are very keen to do some space applications, and not just that, improve the life of people here. So satellites improve life. This is very apt topic, and it's concluded, and I hereby declare the event concluded. And if any students want to stay longer and ask a few questions, they can stay back. Thank you very much, and have a nice day, all of you.
Thank you.
Thank you, sir.
Thank you.
Prachit? Hey, Prachit?
Yes, ma'am. Hello.
Yeah, thank you very much for being there and handling all this,
No,
and
no,
Richal
thank
and the
you.
entire team, Astro Edu, all of you. And I'm sure you had to start your day very early, but how are things at your end? Hope everything is great.
Yes, everything is fine.
Good,
Things
good.
are really nice.
And
We are
I'm sure
actually
you are
starting
enjoying.
in-person classes very soon from starting this Monday.
Cool, cool. Yes, good. Great to know that.
Yes.
And yeah, we can request the students to put their questions. They'll put up here, and then we'll email and share them with Kale sir. And I'm sure he'll get back to us. And one day we can also, like post-pandemic, I'm sure we can do a visit to the universities, SPPUs, ISRO cell, and have a look at stuff, and also industry visits and ISRO visit to NASA, European Space Agency. There are so many plans, but I'm sure they'll all flood now after the pandemic thing. This is over. Thank you once again. Thank you very much, all of you.
Okay. So I think people have your email, right, Richal?
Yes,
Yes.
yes. I've
Yeah.
shared ma'am's email address, mine, and I think yours as well.
Okay. Yeah. So shall I end the call?
Oh, yes. So it was a successful space week, and I'm sure you'll do, and you are doing something or the other at your own end. So this will go. Thank you. Thank you very much.
Thank
Have a
you,
nice day.
everyone.
Bye
Thank
bye.
you.
Take care.
Bye bye. Okay.
Stay safe.
So I think people have your email, right, Richal?
Yes,
Yes.
yes. I've
Yeah.
shared ma'am's email address, mine, and I think yours as well.
Okay. Yeah. So shall I end the call?
Oh, yes. So it was a successful space week, and I'm sure you'll do, and you are doing something or the other at your own end. So this will go. Thank you. Thank you very much.
Thank
Have a
you,
nice day.
everyone.
Bye
Thank
bye.
you.
Take care.
Bye bye. Okay.
Stay safe.
So I think people have your email, right, Richal?
Yes,
Yes.
yes.